Our goal for the previous lesson and today's lesson is to prove the following theorem using a tool from Abstract Algebra, namely maximal ideals. And here's the theorem. Let f be a field and fix a polynomial g of x in the polynomial ring f bracket x. First part of the theorem says if g of x is factorable, then the corresponding quotient ring is not a field. And the second part says if g of x is unfactorable, then the corresponding quotient ring is a field. To get us started, here are a couple of opening questions. First, what does it mean that 5z is a maximal ideal of z? Second question, is 12z maximal in z? So if you could pause the video to answer these questions, then we will go over them shortly. To recall what a maximal ideal is, let's start with 12z, which is not maximal. And that's because we can find another ideal, say 4z, that is strictly between 12z and z. In other words, 4z fits in between 12z and z, but it is not equal to either one of them. Now, this isn't possible with 5z. In other words, there is no ideal that's strictly between 5z and z, and that's why we say that 5z is a maximal ideal of z. And once again, here's the definition of a maximal ideal. Let M be an ideal of a commutative ring R with M not equal to R. Then we say that M is maximal in R if for any ideal A that's sandwiched between M and R, we must have A equals to M or A equals to R. In other words, the only way in which this ideal A can be sandwiched between M and R is if A is equal to one of the endpoints, namely M or R. And that's another way of saying that, once again, there is no ideal A that is strictly between M and R. And here's today's main theorem. Let M be an ideal of a commutative ring R. Part 1 of the theorem says if M is not maximal in R, then the quotient ring R mod M is not a field. And an example would be, for instance, we've seen that 12z is not maximal in z, and therefore z mod 12z is not a field. And how do we know? Well, because z mod 12z is isomorphic to z12, and we know that z12 isn't a field. For instance, it has 0 divisors. In z12, 3 times 4 is equal to 0. And since z12 has 0 divisors, it can't be a field. And because z12 isn't a field, z mod 12z is not a field either. But notice that part 1 of the theorem contains a couple of nots in its statement. And so as we typically do in these scenarios, let's go ahead and prove the contrapositive. In other words, if R mod M is a field, then M is maximal in R. That's what we'll prove in today's lesson. And the second part of this theorem says, if M is maximal in R, then R mod M is a field. So an example would be, well, we've seen that 5z is maximal in z, and therefore z mod 5z must be a field. And how do we know? Well, z mod 5z is isomorphic to z5, which we know is a field because all of the non-zero elements of z5, namely 1 through 4, are units. And since z5 is a field, z mod 5z must be a field as well. So the focus of today's classwork will be on proving this theorem about maximal ideals. And what's the upside of this theorem? Well, let's put it all together. Last time, we proved the following theorem. Let f be a field and fix a polynomial g of x in f bracket x. If g of x is factorable, then the ideal bracket g of x is not maximal in the polynomial ring f bracket x. If g of x is unfactorable, then bracket g of x is maximal in f bracket x. And today, we'll prove the following. Let M be an ideal of a commutative ring R. If M is not maximal in R, then the quotient ring R mod M is not a field. If M is maximal in R, then R mod M is a field. And now we will connect these two theorems while using the polynomial ring f bracket x for R and the principal ideal bracket g of x for M. And let's see what happens. Well, the first theorem says if g of x is factorable, then bracket g of x is not maximal in f bracket x. But if bracket g of x is not maximal in f bracket x, then the quotient ring f bracket x mod bracket g of x is not a field. And the second part says if g of x is unfactorable, then bracket g of x is maximal in f bracket x. And then if bracket g of x is maximal in f bracket x, then the quotient ring is a field. In other words, by connecting these two theorems together, we obtain our desired goal, the proof that we've been trying to prove using the tool from Abstract Algebra, namely maximal ideals. And now, please pause the video and work on day 37 classwork. And afterwards, we will review some of the problems and concepts. Once again, by connecting the first two theorems on this slide, we obtain our main theorem about the polynomial quotient ring and when it is or is not a field. In the next slide, we will discuss the proof of the second part of today's theorem. For the proof of the first part, please see chapter 37 of the textbook. We will prove the following claim. If M is maximal in R, then R mod M is a field. And here we will discuss an outline of its proof. Now, our goal is to show that R mod M is a field. And to do that, we consider a non-zero element of the quotient ring R mod M. And thus, A is not an element of the ideal M, which we'll use later in the proof. Now, in the very last step, we will show that this non-zero element A plus M has a multiplicative inverse, which shows that the quotient ring R mod M is a field. And now here's the trickiest step of the proof. Define the set M plus bracket A, which contains elements that are sum of an element in the ideal M with an element in the ideal bracket A. This is a sum of two ideals, which also happens to be an ideal, and I'll leave it up to you to prove that technical detail. And now, as we showed in the classwork, this ideal that we just defined, M plus bracket A, is sandwiched between our ideal M and the ring R. But our hypothesis says that M is maximal in R. And since our new ideal, M plus bracket A, is sandwiched between M and R, it must be the case that M plus bracket A is equal to one of the endpoints, either M or R. And so that's our next step in the outline. Since M is maximal, m plus bracket a must equal either m or r. And our next task is to figure out which one it's equal to. And here's where our earlier observation that element A is not contained in the ideal M will play a role. Now we can write A as 0 plus A times 1, which has the form of an element in our ideal M plus bracket A. And therefore, A is contained in M plus bracket A. But we saw earlier that A is not contained in the ideal M. And therefore, M plus bracket A and M cannot be the same ideal because one of them contains the element A while the other one does not. Since M plus bracket A doesn't equal one of the endpoints M, it must equal the other endpoint, namely R. Now, R is the whole ring, so in particular, it contains the multiplicative identity element 1, and therefore 1 is also contained in M plus bracket A, which implies that we can write 1 as little m plus A times little r, where little m is in the ideal capital M, and little r is in the ring capital R. And therefore, we conclude that the cosets AR plus M and 1 plus M are equal to each other. And that's because the difference of their coset representatives is 1 minus AR. And by rearranging this equation, 1 minus AR is equal to little m, which is contained in the ideal capital M. But we can rewrite this left-hand side, the coset AR plus M, as a product of the cosets A plus M times R plus M, and that equals 1 plus M. And therefore, A plus M has a multiplicative inverse, namely R plus M, which implies that our quotient ring R mod M is indeed a field. Now, as mentioned earlier, coming up with this ideal M plus bracket A, the sum of two ideals, that is perhaps the most tricky part of this proof. And please take a look at chapter 37 in the textbook for a motivation behind coming up with that step. But that's the end of this proof outline, and also the end of this lesson, and the end of this course. So thank you for watching.